So essentially here, I would like you to give me the mechanism of a hydrolysis of acyl chlorides to make carboxylic acid. So here's a general acyl chloride. Taking you the steps, so let's go through nucleophilic attack of water. So there's some water coming in with its lone pairs. This carbon is of course slightly positive. Electrons love that slightly positive. Go on to the carbon there. The carbon says to the oxygen, take the pi electrons and make them p electrons on a lone pair. So we get the classic tetrahedral intermediate that we've seen with the carbonyl groups for aldehydes and ketones. And now we're seeing with the carbonyl group in these acid and acid derivatives. So there's our tetrahedral intermediate. Next step is going to be deprotonation of the water. So now we're going to have an anionic tetrahedral intermediate because we're removing the plus from there. So we'll just have another water coming in to deprotonate the water. Thus would give us H3O plus when it does that. So there you go. Electrons that were here go on to the oxygen as a lone pair. So there is our nice anionic tetrahedral intermediate. And of course, we've made H3O plus as we said. Stage 3, leaving of the beta leaving group. Well, we've got groups that can leave. O minus, that ain't going to leave. R, that ain't going to leave. OH minus, well, could leave, except it's a really bad leaving group, or Cl minus, what a super duper leaving group. So the Cl minus is now going to leave. And so the way that we draw that is the electrons, extra electrons on the oxygen come in to make the carbonyl group, thus making this carbon now happy. So it's quite happy for the chlorine to leave, thus making us the carboxylic acid and the chloride leaving group. That was such fun. Let's react acyl chloride with ammonia to produce an amide. Again, give you the steps. Nucleophilic attack of ammonia. So there's the ammonia comes in with its electrons, which love that slightly positive carbon. Going again to the tetrahedral intermediate. Now we're going to deprotonate the ammonia, but we'll deprotonate the ammonia by another ammonia molecule. So there's the tetrahedral intermediate. Another ammonia comes in, grabs itself one of those hydrogens to make NH4+. And now we've got that anionic tetrahedral intermediate. This is the bit we're interested in. So one of these groups is going to leave. Well, R's not going to leave. O minus isn't going to leave. NH2 minus isn't going to leave. But again, chloride, super duper wonderful leaving group. So that will leave, as shown by these arrows, giving you the amide. Carbon C double bond O with the NH2. Okay, it's mechanisms for these nucleophilic substitutions, very, very similar to that for the nucleophilic addition, going through that all-important tetrahedral intermediate. And then the only question, once you have the tetrahedral intermediate, is are you going to protonate the oxygen? That's what usually happens when you do the nucleophilic addition. Or are you just going to lose a good leaving group, like the chloride here, leaving you behind with just a substitution?